Okay, we're in Chapter 10, Section 2 of Barnett, Infinite Limits and Limits at Infinity. So the goals for this section are to understand the concept of infinite limits first, and then to be able to locate vertical asymptotes, as well as learn about vertical asymptotes, calculate limits at infinity, and know what horizontal asymptotes are. So those are going to be our goals for this section that we'll go over in several videos. So there are various possibilities under which this limit, as x approaches some number a of a function, does not exist. For example, if one-sided limits are different and x equal to a, then the limit doesn't exist. Another situation which we'll encounter is where a limit may fail to exist, and that situation involves functions whose values become very large as x approaches a. The special symbol we use, infinity, is used to describe this type of behavior. Okay, now to illustrate this case, the best thing to do is let's look at an example. So here's an example. The function f of x is equal to 1 over x minus 1. Okay, now you all know that this function is discontinuous at x equal to 1, obviously, because when we plug in 1, we get 1 over 0. Now, as x approaches 1 from the right, the values of f of x are positive, and they become larger and larger. And you could see on the graph, here's the graph of f of x equals 1 over x minus 1. As you approach 1 from the right, so we're going right to left, the function gets larger and larger and larger in value. So we say f of x increases without bound. Okay, and how do we write this symbolically? We say f of x equals 1 over x minus 1 approaches infinity as x approaches 1 from the right. Now, you all know infinity is not a real number. The limit above does not really exist, right? I mean, infinity is not an actual number. If we were to say the limit as x approaches 1 from the right of 1 over x minus 1, we would say does not exist. Okay? But just because we say equals to infinity, we just simply say equals to infinity because this describes the manner in which the limit fails to exist. Okay? It gives us more information. It tells us about the behavior of this function. Well, we call this an infinite limit. Okay? So, as we continue this example, as x approaches 1 from the left, on the other hand, right? So we're going now left to right. We approach from the left. Okay? The values of f of x are negative, and they become larger and larger in absolute value, right? In other words, they're getting more and more negative here, but in absolute value, they're just getting larger. That is, we say f of x decreases through negative values without bound. F of x decreases through negative values without bound. How do we write this symbolically? We say f of x equals 1 over x minus 1 approaches negative infinity as x approaches 1 from the left. The graph of this function is shown here. Notice that the limit at the point 1, right, this is x equals to 1, that limit does not exist. Okay? So keep that in mind. Alright? Now, let's give a definition, formal definition for what's a vertical asymptote. Alright, so the vertical line x equals to a is called a vertical asymptote for the graph of y equals f of x if f of x approaches infinity or f of x approaches negative infinity as x approaches a from the right or from the left. That is, f of x either increases or decreases without bound as x approaches a from the right or from the left. That's what that really means. Think about this term, increases or decreases without bound, right? It just keeps getting bigger and bigger and bigger. Now, it says note, if any one of the 4 possibilities is satisfied, this makes x equals to a vertical asymptote. So any one of these 4 cases illustrated here needs to be satisfied. Even though we need any one of these 4, most of the time the limit will be infinite, positive or negative on both sides. But it doesn't have to be. Okay, so any one of the 4 cases is good enough for x equals a to be a vertical asymptote. Now, how do we locate these vertical asymptotes? Well, if a function f is continuous at x equal to a, continuous at a point, which we'll talk about later in 10.3, then it turns out that the limit as x approaches a of f of x is equal to the limit as x approaches a from the right of f of x, or it's equal to the limit as x approaches a from the left of f of x, and all 3 of those are equal to f of a itself. Okay, so that turns out to be a true fact. Okay, so like I said, we'll define continuous at a point later, and this will show up again. But since all of the above limits exist and are finite, for now, f cannot have a vertical asymptote at x equals to a. In order for f to have a vertical asymptote at a point x equals to a, at least one of the limits above must be an infinite limit, and f must be discontinuous at x equal to a. Well, we've seen already that polynomial functions, okay, those are continuous for all real numbers, right? We saw that in the previous section. So we could say a polynomial has no vertical asymptote. Polynomial can never have a vertical asymptote on its graph because it's always continuous. Likewise, the other big branch of functions that we'll look at in our class are rational functions. Since a rational function is discontinuous only at the zeros of the denominator, a vertical asymptote of a rational function can only occur at a zero of its denominator. Once again, a vertical asymptote of a rational function can only occur at a zero of its denominator. Okay, so the following is a simple procedure, in fact, for how you can locate vertical asymptotes of rational functions. Think of the function as n of x over d of x, right? We use n to represent numerator and d to represent denominator. So break the rational function into two polynomials, n of x over d of x. All right? Now, if d of c is equal to 0, right? So if the denominator is 0 at the value c, and the numerator is not 0 at the same value c, then the line x equals to c is a vertical asymptote of the graph of f. However, you have to be careful. You have to check both. Because if both the denominator and the numerator are 0 at c, there may or may not be a vertical asymptote at x equal to c. Let's investigate this further here by doing an example. Okay? Take a look at this function. The function is f of x equals x squared plus x minus 2 over x squared minus 1. And it says, describe the behavior of f at each point of discontinuity. Use infinity and negative infinity when appropriate. Identify all vertical asymptotes. So let's start with the points of discontinuity. Where is this function discontinuous? And you might be saying, well, if I take the numerator to be x squared plus x minus 2 and d of x to be x squared minus 1, obviously if I factor the denominator, right, x squared minus 1, that's the same as x plus 1 times x minus 1. It's a difference of squares. This has two zeros at negative 1 and 1. And these are the points of discontinuity of f, because that's where the denominator will be 0. Okay, so now that I've identified those, let's see what's happening for each one of those. Okay, so if we take a look at the next slide here, the denominator at negative 1 is 0, but the numerator at negative 1 is not. You get negative 2. So for the numerator, it was x squared plus x minus 2. When you plug in negative 1, you get negative 1 squared plus negative 1 minus 2. You get negative 2. So you get something different than 0. So by the theorem, the line x equals to negative 1 is a vertical asymptote. That's what we get. Why? Because the denominator is 0 there and the numerator is not 0 there. That's why the line is a vertical asymptote. Now, what if we consider the other 0 that we obtain, x equals to 1, the other case? This time, notice that the numerator is 0. The numerator at 1 is 0, and the denominator at 1 is 0. So the theorem does not apply. What we would have to do instead is we're going to have to use algebraic simplification again to investigate the behavior of the function at that point, x equals to 1. So, how do we do it? Well, we factor out the top and bottom as much as we can, as it's shown here. And as you could tell, x squared plus x minus 2 can be factored to x minus 1 times x plus 2, and x squared minus 1 can be factored to x minus 1 and x plus 1. Once these two linear terms cancel, we could plug in 1, and we'll see that we get 3 halves. So since the limit exists as x approaches 1, it's equal to 3 halves, f does not have a vertical asymptote at that point, x equal to 1. The graph of f, in fact, is shown on the next slide, where it should be obvious where we have a vertical asymptote at negative 1, and that at 1 we get a value close to 3 halves, right? But we have a point of discontinuity there, just no vertical asymptote.